start the recording. Its therapeutic indication is it is an oral contraceptive. So this is what we mean by an oral contraceptive. It's basically, if you look in this inner dial, that's a little calendar there, and basically these pills, which contain 0.035 milligrams per pill of this active pharmaceutical ingredient, basically what this molecule is, it mimics a biological hormone and basically tricks the human female body into thinking that it's already pregnant. And so what will happen on the monthly cycle, it will go through its process. So this molecule wasn't basically, we'll say, synthesized in a lab until the late 40s, early 50s. And then this gentleman here, Professor Carl Djerassi of Stanford, was one of the primary scientists responsible for its synthesis. So while it is based on a steroid nucleus, which is a natural product, it is a synthetic molecule, meaning that this molecule does not exist anywhere on Earth outside of it being produced in a lab. So we're going to look at different functional groups today in relation to the molecule itself. So let's go ahead and get to a couple questions about it. So our first LEAP question about bonding and hybridization. So the birth control steroid ethinyl estradiol is shown. How many pi bonds does the molecule contain? You can put a number in the chat box or a letter corresponding to the correct answer. So one thing I really want to encourage you is for these questions, make sure you really understand what the intent of the question is, and that you give it like your best shot in terms of what you think the answer is. So again, the exams will be formatted a bit differently. The exams will look like your Wiley Plus homework sets, essentially. So the questions I'm asking you here are questions I created myself. And in my opinion, these questions are a little bit more difficult. So the correct answer is 5. Let's go ahead and point those out. We have 1, 2, 3, 4, 5. So within this molecule, we have all 3 different types of carbon hybridization. We have sp3, sp2, and sp. So on your phone, if you move that molecule around, you should get an understanding of how the carbon hybridization affects the shape of the functional group. So if you're looking at this ring here, this ring with 3 pi bonds, that ring is called benzene. So I'm going to hold that ring up on the camera here. The benzene ring, if we're looking at it sort of edge on, is flat. So right here. So the benzene ring consists of 6 sp2 hybridized carbons. An sp2 hybridized carbon is trigonal planar. So let's just recap. sp3 is tetrahedral, sp2 trigonal planar, and sp is linear. That's the geometry, and the geometry gives rise to the shape. So a triple bond consists of a sigma bond plus 2 pi bonds. A double bond consists of a sigma bond and 1 pi bond. And so again, we have sp3, that's tetrahedral. sp2 is trigonal planar, and sp is linear. So you can see just by looking at the structure, we're rapidly accumulating a lot of knowledge. What is the hybridization of the carbon? How does that give rise to the shape? And all of these things are going to overlay on each other as we build through the semester. Okay, so our next question, it's changed a little bit. How many rings does the molecule contain? How many rings? So the correct answer is B as in boy, or 4. We have 1, 2, 3, 4 rings. So if we add those two numbers together, 5 plus 4 is 9. What you've just done is an exercise in determining degrees of unsaturation. So you've done it visually. You've counted the pi bonds, you've counted the rings. So I'm going to post a recorded lecture in a little bit after this about how we do that with molecular formula. So if you are not given the structure itself, if you were just given a molecular formula, how could you do the same thing? And the reason that degrees of unsaturation is so important to us this semester is that that number that we've determined and we've visually counted, that tells us a functional group. So it tells us a functional group. We can then start making connections between that functional group, the shape of the molecule, the reactivity of the functional group, and how we can make further transformations. So here's our next question. How many sp2 hybridized carbon atoms does the molecule contain? sp2 hybridized carbon atoms. So we had some 3s showing up. Looks like we're on a run of 6s here. The correct answer is 6. And again, an sp2 hybridized carbon sp3 has 4 sigma bonds, sp2 has 3 sigma bonds, plus 1 pi bond. sp has 2 sigma plus 2 pi bonds. So in the chat there, we're asking about sp2, so we're looking for carbon atoms that have 3 sigma bonds, 1 pi bond. So we have 1, 2, 3, 4, 5, 6. So they're all contained in this benzene ring. How many sp hybridized carbon atoms do we have? sp present in the molecule. So there are 2 of them. Those 2 are located in this functional group. So that functional group is called an alkyne. So there are many layers of understanding structure in communicating it. So when you see the word alkyne, what you should think of is a carbon-carbon triple bond. When you think of the word benzene, you should think of this structure here, a 6-membered ring with 3 pi bonds. So Hannah's asking, this functional group right here, this alkyne, there's one, there's two sp hybridized carbons. A carbon-carbon triple bond is called an alkyne. So we're going to use these terms to communicate structure. So as time progresses through the semester, if I say, here is ethynyl estradiol, let's look at functionalizing the alkyne of this molecule. So when I say alkyne, your eye should be drawn to this part of the molecule here. Any questions before we transition into a learning activity? Elizabeth is asking, can it be pronounced alkene, or is that something different? It is something different. So as I just typed in the chat box, alkane, alkene, alkyne. So there's how you differentiate those. Alkane has sp3 hybridized carbon. Alkene has sp2. Alkyne has sp. And again, the lecture that I post on YouTube in a little bit will explain all that. So again, while subtle, those names do make a difference, and you need to understand that when we use those terms, it should visually in your mind invoke what the connectivity of those atoms are. So I'm going to transition into this slide here called Moving On Up. And just a brief yes or no in the chat. How many of you have heard of Bloom's taxonomy? So I'm seeing more no's than yeses. So I want to briefly just explain what this is and how it relates to this term learning outcomes that I'm using quite a bit in the pre-recorded lectures. Bloom's taxonomy is basically this pyramid shown here. And there's what, 6, this one shows 6 different categories. We're going to start at the bottom with remember, then we move up to understand, then apply, analyze, evaluate, create. So the relevance of this to you is the following. In general chemistry, you're hovering around remember, understand, apply. For organic chemistry, we're moving towards the top of this pyramid here. Apply, analyze, evaluate, create. Create maybe more a little bit in 256, but really we want in our learning efforts to be applying, analyzing, and evaluating. So the remembering and understanding, that's going to be assumed on my part. What I'm looking for you to do is use information in new situations, draw connections amongst ideas, and justify a stand or decision. These words here are the active verbs. And so as you see in the syllabus, in the Canvas module, and then the lecture recordings, I put these words in bold. These are things that you need to be able to do to show you understand the material. So we're really looking to apply, analyze, and evaluate. And as you progress through your undergraduate degree, really you're hovering towards the top of this pyramid. You're leaving sort of this behind in a sense. It's still important, but what you're asked to do mentally is more in this arena. So let's now look at an AQ activity. AQ is a 3-semester program that I went through to help bring learning activities into the lecture, and one of them is ThinkPair Share. The prompt that you are given is the following. So given a molecular formula of C4H10, draw all the possible constitutional isomers in the bond line convention. So take a couple minutes, and then as you draw structures on your paper, if you want to put your camera on, show it up to the camera, I'll take a look at it and comment. So you're given this formula, C4H10, start drawing some structures. Remember that the structures have to obey Lewis dot rules and the octet rule. Some additional prompts. What is the mass of C4H10? How many unique carbons does each structure have? How many unique sets? What are the ratio of those sets? And then look up the melting and boiling points. Boiling points, that should be boiling points. You can check Wikipedia for that. That's a pretty good place. So take some time, if you're ready, to show the structures in your webcam. So Ashley, if you can move it back a little bit. So yeah, that's one of them. So what is the intent of this question? So I apologize. My Wi-Fi is like really, really bad today. So Hannah, I see you're holding something in, but it's sort of pixelated. If you can maybe move back a little bit, maybe tilt your page down. Yeah, it's too pixely for me, so I apologize about that. I sort of see a little bit now. It came into focus. Yeah, that looks correct, Hannah. That's one of them. So what is the intent of this question? You're given a molecular formula, C4H10. So Taka, you have both correct. There are two. What this molecular formula, Aislinn, yeah, that looked correct. What this molecular formula does not tell you is how those carbons are bonded and how they're bonded to the hydrogen. So you can actually have more than one constitutional isomer. And that's really what you're trying to think your way through is, what are all the possible ways I can do this and still obey Lewis dot and the octet rule? So I think if you want to see other people, you have to click on their name. So Christopher, yes, I've been having some issues with Canvas as well. It took me a little bit to get logged in. So Ian looks like he has both of them written down in the bond line. Those look correct. So think about these other prompts. How many unique carbons does each have? How many unique sets of hydrogens, and what is the ratio? And then look at Wikipedia. What's the melting and boiling points of those? Again, the reason I'm asking you to do this is that for a constitutional isomer, if they're both C4H10, how can you differentiate those two substances? Yes, the melting and boiling points will be different because the intermolecular attractive forces are different. But these prompts here, the unique carbons, unique hydrogens, will also differentiate them. So Elizabeth is asking, how many bonds can hydrogen have? So does anyone want to help out in the chat? So one. So hydrogen can only have one bond. So if you propose a structure that has two bonds to hydrogen, using metacognition, you should recognize that structure is incorrect. So if anyone knows the name of, so I'll write it in the chat, name of the linear isomer. What is the name of the linear isomer? So Taka wrote butane. Butane is correct. What is the name of the branched isomer? So we have isobutane. That's a common name that's acceptable. Methylpropane, we have 2-methylpropane. That's a little bit more correct. The way we're going to learn how to name this, it would be 2. We have some variations of the name. There's no space between the methyl and the propane, as Taka wrote. It's 2-methylpropane, all one sort of word. So I don't expect you to know that right now. Again, we're going to go through that over the course of the semester. The repetition that we present through these, your textbook reading, the chats, the lectures are all important. So again, don't get frustrated or anything like that if you don't know that right now. Let me just explain to you some of the logic that's going on here. Notice the ending of those isomer names. They end with ANE. From the ending, you can then know that they are alkanes. And what did we just say before about alkanes? They all have sp3 hybridized carbon. So these are the connections that you're going to want to be making in this course. Even though a simple name alkane, what is the information you can extract from that name? So let me ask you, for butane, how many unique type of carbon does butane have? There are 2. So my next question is, what type are they? Remember the exercise we did before? When we classified carbon, we had methyl, methylene, methine. What type of carbon are they? So they are methyl and methylene. That's correct. Yes, they are sp3 hybridized. So for 2-methylpropane, how many unique type of carbon do you have? So you also have 2. Now what type are they? So they are methyl and methine. So Garima asks, how do we know the unique type? You know, I'll point that out on the next slide. So notice what we just did is a thought experiment, even though we wrote some stuff on paper. We proposed two constitutional isomers. We differentiated them according to their name. Now, even though they each have two unique type of carbon, we've differentiated them about how those carbons are classified. So for butane, how many unique type of hydrogen does butane have? So butane has two. Now what I want you to do is, of those two types, what is the ratio of those types of hydrogens to one another? So 6 to 4, or if we reduce it 3 to 2, that is correct. We had two types of hydrogen. There are methyl groups, and then there's methylene groups. There are 6 methyl hydrogens and 4 methylene hydrogens. So Camille asks, am I missing something? How do you tell if they're unique? The simplest test of uniqueness is really you're looking for a mirror plane. So a mirror plane of symmetry. The terminal carbons end up being the same because they mirror each other. The internal methylenes are the same because they mirror each other as well. So before I put the structures up, let's do the same for 2-methyl propane. How many unique sets of hydrogen atoms do you see? Again, there's 2, and then what is the ratio? It's 9 to 1. One type are methyl groups. There's 3 of them. They're all equivalent. 3 times 3 is 9, plus the methine is 1. Notice that for the total hydrogen count, it's what we see in the molecular formula. So Aiden asks, could you name it methylpropane? No, you have to use the number 2. And again, we'll get to those rules, but you have to use the number. The number 2 is a locant number of what comes after. The 2 tells you where the methyl group is on the parent propane chain. So here are those constitutional isomers. Butane, the melting point of -140, the boiling point of -1. There's what you guys just determined. There's 2-methylpropane, the melting point of -159, the boiling point of -11. So here's the ball and stick formula. So in terms of the symmetry, this methyl group is equivalent to that. This methylene is equivalent to that. The mirror plane bisects the central carbon-carbon bond. For 2-methylpropane, the 3 methyl groups are equivalent, and then the methine is different. So what are you conceptually doing? As physicists like to say, this is a thought experiment. When you do this uniqueness test, really what I'm asking you to do is, in your mind, think about how the carbon NMR is going to look and how the proton or hydrogen NMR is going to look. So the carbon NMR of each of these should show 2 peaks. The proton NMR is also going to show 2 peaks, but the integration or ratios are now different. You have 6:4 and 9:1. So the next 2 slides are basically just going to show you what is shown here is the molecule again, and then in red down here are these 2 lines that you see. This is a carbon NMR. Remember, you said you should see two unique carbons, and that's exactly what you see. This signal here and this signal here. The signals are resolved from one another because the carbons are in different environments. So when I ask you about uniqueness, really what you're doing is you're thinking about the carbon in proton NMR. So notice sort of the ratio in the carbon is equal for butane. Then when we go to 2-methylpropane, we also said there's 2, but now sort of the ratio is different because we have 3 of one type and 1 of another type. So conceptually, that's really what you're doing with uniqueness, is you're thinking about spectroscopy, and that's going to be the foundation for Module 2. Any questions on this activity before we move on? So for this next activity, we're not going to spend time doing it during the chat. It's meant for you to sort of follow up on the chat, but it's another ThinkPair Share. Now the molecular formula has changed to C4H8. Think about all the constitutional isomers you can draw for that. C4H8. As you're doing it, try to answer the following questions. How many unique carbons does each isomer have? How many unique sets of hydrogens? What are the ratios? So spend some time after this chat doing that. But what I'd like to do now is move on to the workbook and do some problems in there. If I can get it to show up. All right. So hopefully at this point you all can see the workbook. So if you can't either say something in the chat or unmute yourself. But we're on page 4 of chapter 1, bond line drawings. It says for each of the following molecules, count the number of hydrogen atoms connected to each carbon atom. So let's start with 1.13. So for this carbon right here, how many hydrogen atoms are bonded to that carbon? So we have 0. Now let me ask you a different question. What is the hybridization of that carbon? So we got a couple of sp2s. And how do you know it's sp2? Why are you saying sp2? What is your reasoning? There's the presence of 1 double bond or 3 sigma plus 1 pi bond. So Kenneth, there's 3 sigma and 1 pi. There is not 2 pi, 2 sigma. That would be an sp hybridized carbon. What about this? Let's go around clockwise. What about that carbon? How many hydrogens are bonded to that carbon? So it is 1. Hannah revised her response. What's the hybridization of that carbon? sp2, that's correct. How many hydrogens on that carbon? It's 1 as well. It's also sp2. How many hydrogens there? Two here. Got some more 2s. And then the last one, that's also 2. So before we move on, how many unique type of carbon atoms do you see in that structure? Unique type of carbons. So we're getting some 3s, some 4s. The hybridization of the carbons with 2 hydrogens is sp3. The correct answer for unique type of carbon is 6. Even though the structure has 1, 2, 3 CH2 groups, all of those CH2 groups are different. Why is there no symmetry? The molecule has a plane of symmetry within the plane of the paper, but there's no symmetry perpendicular. The perpendicular plane of symmetry is typically what will reduce the carbon count from what you see in the molecular formula to something lower. So how are we determining this so that you know? So maybe with this burgundy marker here, I'm going to start at this carbon. We said that's sp2 hybridized. It has no hydrogens, so that's a unique type of carbon. I'm going to go clockwise. This carbon here, that has a hydrogen on it. It's sp2 hybridized. That's different from the first one, right? The next carbon here, even though it's sp2 and it has a single hydrogen, it's not the same as the second one because its relation to the first carbon is different. Now we have an sp3 hybridized carbon. That's different from all the prior ones. It has 2 hydrogens. This is also sp3. It has 2 hydrogens, but it's not the same as the prior one because it took us sort of longer to get to that one than it did to this one. So those can't be the same. Finally, sp3 hybridized carbon with 2 hydrogens. And again, that's different because its relationship to the first carbon is also different. So that's how we end up with this number 6. So I encourage you to do that for the rest of these. what I'm going to do is move on to a different type of problem now so that we can sort of go through and you can see the thought process for solving these different types. Any questions before we move on from that one, though? So yes, every carbon in this structure is unique. Generally speaking, you have to look at the structure, see if there's a mirror plane of symmetry, and that will help you determine uniqueness. So our next section here is how to draw bond line drawings. So Sarah's asking how many unique type of hydrogen. So this carbon atom did not have any hydrogens. So for unique type of hydrogen, we have 1, 2, 3, 4, 5. And then what we're doing in terms of the ratio, we're just counting how many there are. 1 to 1 to 2 to 2 to 2. If you add that up, that should be the total number of hydrogens in the molecule. So we have 2, 4, 6. We have 8 total hydrogens in the molecule. So let's move on to one of these, how to draw bond line drawings. So this problem says for each structure below, draw a bond line drawing in the box provided. So maybe take about 30 seconds, and given this structure, how are you going to represent it in this box where basically the carbon atoms, you no longer draw a C, you draw a bond line. The hydrogen atoms are now all implicit. So Aiden drew a plus sign, and that would be correct. So if I do this, 1, 2, 3, I'm going to just draw this out so everyone can see. I'm drawing, there's bonds 1 and 2. There's bonds 3. So off carbon 2, we have a methyl group. Then off carbon 2, we have another one. So that's one way we could do it. Or as Aiden drew it, you could basically draw that. It would be the same thing. So one thing you have to realize, how we draw things, if this and this are the same thing, is one more or less correct, as Hannah asks? I would say this one is probably more correct. And even though it's subtle, why is that reason? Again, this is an alkane, correct? And we said for alkanes, there's sp3 hybridized carbon. So we want to show the carbons with tetrahedral geometry. And this one's closer to doing that. So the reason I say that is because it more mimics the natural bond angle. The bond angle of this one sort of looks like 90 degrees. So as we refine how we interpret and draw things, we're probably going to want to stick more towards something that mimics the normal hybridization bond angle. So why don't we try this next one? How would you represent that with bond line? And again, you can draw it, show it up to your webcam. Blakely, Blakely, you're correct. Taka, you're missing a carbon on the linear portion of your molecule. James, yours is correct. Hannah, if you could move yours over a little bit. Maybe a little closer. Aiden, yours is correct. Hannah, you went away. Hannah, yours looks correct now. Taka, yours is correct. So yeah, let's go ahead and convert that. So if we're looking at this chain, we have 1, 2, 3, 4, 5, 6 carbons. Carbon 4 we see has a pi bond to oxygen. Then we see carbon 5 also has another methyl group. So that's a way to convert from this sort of Lewis structure to the bond line structure. So we're about out of time. Again, I apologize for the Wi-Fi issues I was having, but this is the format that we'll do for the chat. We'll go through a molecule of the lecture, some questions, a learning activity, then we'll do some workbook stuff. I'm going to post another recorded lecture in YouTube in about an hour or so, so look for that. Try to start working on your homework sets. Those are due next Monday at 11. I'll explain a little bit more about the exams over the course of this week. But other than that, shoot me an email if you have any questions. I'm going to go ahead and wrap up this chat session, and we'll see you Wednesday.